Welcome back to another Explainer. Today, we're diving straight into the core mechanics of a true bench staple, the BC557 transistor. If you've ever rummaged through a drawer of spare components, or maybe skimmed a schematic for a small electronics project, I guarantee you've seen this little black piece of silicon looking back at you. We're going to take its dry, technical datasheet and transform it into a super practical guide for your next circuit build. We'll break down exactly what it is, how it ticks, and why it's just so incredibly popular.
Here's the roadmap for today. First, we'll officially meet the BC557. Then, we'll unpack exactly how it works. Third, we'll explore how to use it for switching and amplifying signals. After that, we'll cover its key applications and strict limits. And finally, we'll talk about finding the best alternatives when your parts bin is empty.
All right, let's jump right into Section 1. Meet the BC557 Transistor. So the absolute most crucial thing to know right off the bat is that the BC557 is a PNP bipolar junction transistor. Now, PNP just describes the specific arrangement of the semiconductor materials sandwiched inside. It's an absolute staple for small electronic circuits, mostly because it offers a really sweet spot combination. You get a moderate voltage rating, super low current consumption, and remarkably high DC current gain. When you need to process a tiny signal or drive a small subcircuit without hogging power, this is your go-to guy.
Let's look at a quick snapshot of the foundational specs, basically the operating limits right out of the gate. You'll almost always find the BC557 housed in this familiar little plastic TO92 package. By the numbers, we're looking at a maximum collector current of 100 milliamps and a collector-emitter voltage limit of 45 volts. It can safely dissipate about 500 milliwatts of power, and it boasts a transition frequency somewhere in the ballpark of 100 to 150 megahertz, depending on your manufacturer. Oh, and it's tough, operating in extreme temps from -65 all the way up to positive 150 degrees Celsius. These numbers, they are the absolute rules of the road.
Now, here is a really interesting quirk. You might have noticed a final letter at the end of the transistor's name. That actually dictates its DC gain group. If you've got a BC557A, your gain is roughly 110 to 220. The B variant bumps that up to somewhere between 200 and 450. And the C variant, that shoots all the way up from 420 to a massive 800. But here's the catch, and it's a critical one. Having a higher gain doesn't magically let you push past that hard 100 milliamp current limit. It literally just means you need even less base current to max it out.
Moving on to Section 2, how the BC557 works.
Before you even think about plugging anything into a breadboard, you absolutely have to know your pins. When you're looking flat at the front side of that standard TO92 package, you'll generally find the collector as pin 1 on the left, the base as pin 2 in the dead center, and the emitter as pin 3 over on the right. Just a quick heads up though, pin configurations can occasionally vary by manufacturer, so doing a quick double check of your specific datasheet is always a smart move before you heat up the soldering iron.
To make sense of the mechanics of this PNP configuration, I like to just remember a simple three-step sequence. Since it's a PNP transistor, the emitter is usually tied up toward the positive supply. Step 1, when the base voltage drops sufficiently lower than the emitter voltage, boom. Step 2, the transistor turns on. And Step 3, once it's on, a tiny little base current controls a much larger current flowing seamlessly from the emitter right on through to the collector. Bring that base voltage back up close to the emitter, and it shuts right off. Easy, right? Okay, let's get practical with Section 3, switching and amplifying signals.
The BC557 is insanely versatile, basically handing you two major functional roles to play with. First, you can use it as a high-side digital switch for small loads, literally just toggling things on and off. Or, second, you can deploy it as an analog signal amplifier, where tiny, fluctuating inputs turn into much larger proportional outputs. Let's break both of these use cases down.
If you're running it as a switch, here's your high-side circuit path. You wire your positive voltage directly to the emitter. Then, the exact moment your control signal pulls the base sufficiently low, the transistor just opens the floodgates. Current rushes out of the collector, straight through your load, and down into ground. It's a brilliantly simple way to electronically snap power to a small device without needing a mechanical relay.
On the flip side, if you're setting up an amplifier, there's a simple little equation that tells the whole story. The collector current, which we call IC, is roughly equal to the DC gain of the transistor multiplied by that tiny base current. Think about it. If your specific component has a gain of 200, A microscopic base current of just 0.1 milliamps could theoretically control a full 20 milliamp collector current. You're basically taking a tiny whisper at the base and turning it into a shout at the collector.
Which brings us perfectly to Section 4, Key Applications and Limits. Because it's so incredibly cheap and bulletproof to use in discrete circuits, you are going to find the BC557 literally everywhere. It's a massive favorite in the pre-driver stages of audio gear, delicately amplifying small sound signals. You'll catch it acting as a switch in LED driver circuits and relay pre-drivers. It's an absolute staple in sensor networks, logic interfaces, and oscillators. Honestly, it's pretty much the Swiss Army knife for general-purpose maker projects.
But burn this number into your brain, 100 milliamps. The BC557 is absolutely not a power transistor. If you try to push past that strict 100 milliamp maximum collector current, you are going to fry your component and let the magic smoke out faster than you can blink. Because of this hard limit, it is strictly meant for relatively lightweight loads. Do not try to drive heavy DC motors, massive relays, or high-powered LEDs directly with this thing.
In that same vein, the 45-volt collector emitter rating is a total hard boundary. Simply put, never treat this little guy as a high-voltage solution. Keep your supply voltages well underneath that 45-volt ceiling, and your component will stay cool, stable, and happy for a long, long time.
All right, let's wrap things up with Section 5, Finding the Best Alternatives. We've all been there. You're in the zone, your project demands a BC557, you yank open your parts drawer, and it's completely empty. So, what's the game plan? Well, the great news is that in the wide world of discrete transistors, you are spoiled for choice with backup options.
Here's a lineup of your best alternatives. If you just need a rock-solid general-purpose swap, grab a 2N3906. It runs at 40 volts and actually handles up to 200 milliamps. Need a bit more grunt? Step up to a 2N4403 or a BC327. That 2N4403 can muscle up to 600 milliamps. Or you can just stay in the exact same family and use a BC558 or a BC556. Just keep an eye on the specs. The BC558 tops out at 30 volts, while the BC556 gives you way more headroom, up to 65 volts.
But hold on, here is a massive warning. An alternative doesn't automatically mean a perfect drop-in replacement. Just because a transistor handles more current doesn't make it perfectly compatible on your breadboard. You have got to double-check those datasheets. Why? Because some of these alternatives might literally have the collector and emitter pins swapped compared to your BC557. Always verify your pinout, voltage, current, and gain before you even think about hitting the power switch.
And that wraps up our component profile. But I want to leave you with a really fun puzzle to ponder. We talked a lot about the BC557 being a PNP transistor, right? Well, its most famous complementary partner is the BC547. But here's the kicker. The BC547 isn't an electrical twin. It's an NPN transistor, meaning the polarity is the exact opposite. If you were forced to swap your PNP out for that NPN, how entirely would that flip the logic and flow of your circuit design? Think about how the current paths would have to change. I'll leave you to chew on that for your next build. Thanks so much for hanging out with us for this explainer, and we will catch you on the next one.